So I introduced tasks without recording that. Let me quickly show what that does. Now there's a way for programs to have side effects, kind of. And the side effects here are printed in purple. So you can see that this is some file. It requests a random number. Then it wants to print something. Then it wants to read a line. I don't know, it's greater than 10, all right. That's between 1 and 100, I think. So let's actually guess that number. Yeah, and it leaks the memory in the end. Okay, fair. But the idea is that programs can now read lines, they can print something, and they can exit. Now, how does that work? Plum is a completely functional language. Functions are pure, they can't have any side effects. So the way I implemented that is that functions can return a task. Let me actually increase the font size here. Yeah, you can see that the main function here, it takes an int, which is actually ignored, I think, and it returns a task. Now, what is a task, you might ask? Well, a task is this. It's an enum that tells the surrounding VM what to do. So a task can be, I just want to exit. A task can also be, please print something. And then this one actually contains the message to be printed. And then another closure, which should be executed afterwards, that then returns another task. So task really is like a recursive data structure, quite similar to iterators actually. In iterators, iterators are a function that returns an enum, and one of the enum cases has another iterator inside, so another function that then may return another iterator, and so on. And it's similar with tasks. Tasks return another function that the surrounding environment then can call to kind of continue the program. And this task here, like this continuation lambda, doesn't accept anything, but there are others that do accept arguments. For example, if the program wants to request a random number, then it can emit this random task, and this lambda here that accepts an int, a random number, and then it returns another task. Or when it wants to read a line, it has this continuation lambda that takes the line that was read from the user and then returns another task. That means that the entire program is still pure, is still functional, is still, functions don't really have side effects. It's just that the way that the surrounding environment kind of interprets the return value of the program allows it to interact with the program and to do stuff. So basically, Plum programs themselves, they can't really do anything. They can just ask or tell the VM to do something for them and then call them again later. But the important thing is that this transfers control over to the surrounding environment. There is no single function that you can call within Plum and that will then have a side effect. Instead, a function has to return something plus a continuation. All right, so here are some helper functions. For example, print is a function that accepts a message string and the continuation, the then closure, and then it returns a task by actually just creating an enum variant, this print variant here, by putting that in a struct. And similar for these others. So the main function can then result in random, so it asks for a random number, and then given a random number, then calls this ask for number function, which asks the user for a number. And this one accepts the correct number, which will just be the random number we had modulo 100. And we can actually see that here we had like a negative something with a 3 at the end, which means that the number is, what was it, 97. Yeah, that's kind of this one modulo 100. What would be easy to see for a positive number, but yeah. And then this ask for number function prints, hey, what's your guess? And has this continuation, which can then then says, okay, now I want to read a line, giving me a guess. We pass that, then if that's not a valid number, we print that and then ask for a number again. So we call ourselves recursively. If we have a guess, then we compare that to the correct number, offer a helpful message and call ourselves recursively. Or if the number was guessed correctly, then we just print found it and we exit. All right, yeah, this is not so, this is not super exciting. So what I want to do, okay, what are problems with this approach? This approach, first of all, it might seem weird if you come from imperative language or object-oriented languages, where you kind of, functions with side effects are kind of the norm. You can do that. So having to do this kind of dance, feels a bit weird. However, there are other languages that do something similar. For example, I think most functional languages, Rock, Haskell, etc. And this is usually called a monad. Monad in there. Yeah, here it's just an explicit enum. We don't have any abstractions over monad types and so on. It's a bit simpler. It's a bit more down to earth here, but still the concept is there. And again, in other languages, there's precedent for this kind of architecture for side effects. Benefit of this is that because we give full control to the environment can actually, call this lambda here multiple times. If you say, well, please, ask the user for a line, the environment doesn't have to do that. It can just lie and say, I'm going to call this lambda here with maybe yes, and then I'm going to call that lambda again with no. If the program wants to ask for some confirmation, and then the environment can kind of see, what does the program want to do if we would answer yes to the confirmation? What would the program want to do if we answer no? So the environment is in control. That's the key part here. Before going into kind of problems or kind of more syntactic stuff that I wanted to do today, I want to show a quick look at how that is implemented in Zig, in the VM. So we do have the ground VM. That's, that, with all the different instructions, and that didn't really change. What changed, however, is how we deal with that and how we create that. Because now the main VM code here, that reads the bytecode from a file, that runs that, it doesn't use this ground VM directly, but instead it uses this Plum module, which has some parsers for Plum data types. So if we take a look at that, you can see that this just contains a couple of functions for Plum types. It contains ints, and basically this is just a representation of a Plum int, which is an i64. But it has the option to convert that, to parse some bytes from the return stack, basically, from the data stack, into an int. And these have to be exactly 8 bytes. And it can also convert it in int 2 bytes. There are also like pointers, there are buffers of bytes, there are array of bytes, and these are needed to then implement strings. And I think we had that before, actually. The code for parsing strings and the Plum program that returns a string really just returns 24 bytes, which I think are like the pointer of the string and the length, and where we start kind of an offset, something like that. Plus it has code for like duplicating and dropping strings because they are reference counted and so on. So this kind of struct handles all of that. Now I added other functions for lambdas and for tasks. And then lambdas from nothing to task, a lambda from int to task, and a lambda from string to task. And then I think finally I have a program which is actually just a wrapper around bytecode, and it runs, uses this other file, the existing ground VM, to just run the bytecode with the input that we gave converted to bytes. And then the output is passed into a task. So we just assume that the program returns a task. Let's maybe take a look at this task thing. So this this parsing code requires intermittent knowledge of the memory layouting of Plum. So this actually just switches on the last byte of the task, which, because task is an enum in Plum, again, the task is this up here. We can inspect the last byte, and then we know what kind of task we want to perform, and then we construct this zig enum, of the corresponding action. And you can see that this kind of directly mirrors the Plum enum. And if those go out of sync, like, bad things happen. We misinterpret bytes into bad other bytes. Yeah, so that's the idea. I added some code for parsing tasks and lambdas apart from strings. And then the main code uses those. It runs the program on the bytecode that returns a task. And then we switch on that task inside this loop, actually. So you can see that if the program wants to exit, we actually print the task. This just prints the kind of purple thing at the beginning here, kind of telling us, oh, by the way, the program wants to do this, it wants to do that. And this is not super exciting, and it has this weird codes in here that tell the terminal that this should be purple. Please make this purple. And then the actual task, then please don't make things purple anymore. And yeah, it prints exit and then it breaks out of the loop. But for all the other actions here, for example, when printing, we actually print the message. We drop the message because we were given ownership of that. And then we call the then lambda here, which should consume ownership of the lambda's closure. And yeah, that then returns another task. And because we're in this loop, we then switch on that task and see, oh, what else do we want to do? And yeah, there's printing, which is just printing to stand it out. There is random, which gets a random number, which is defined up here using the standard zig default pseudo-random number generator. And then we have a read line, which uses zig's read until the limiter or EOF alloc. Beautiful. And yeah, then it converts that into a Plum string and calls the then lambda with that string. And by the way, because these, you can see that then is of the type lambda from string to task. So this is actually typed. This then.call accepts a Plum string, defined by us in here. And then in here it converts that string to bytes. I think this is really nice. Having this Plum file that contains all the necessary Plum data structures that we need for interoperability and for tasks. And then this main code has a really type-safe way, basically, of using these lambdas, of dropping values, kind of this more high-level working with those Plum values. All right, yeah, and that's basically it. Yeah, so what's a problem with this approach? A problem is that you can see that if we use tasks, the code kind of indents a lot. Just by printing something and then reading a line, we are already, 4 levels indented or something? And that's not super great. So this is actually similar to the problem that JavaScript had for a long time, where they had promises and callbacks. Actually, let me pull up something like JavaScript. Promise then. here we go. So in JavaScript, that's actually quite similar. If you want the system, the event loop, to do something for you, then this is modeled using a promise. And basically, if when you want multiple things to happen one after each other, for example, in our case, we want to print something, and then after that we want to read a line, and then we want to print something else. The way you do that in JavaScript as well is you would have to chain promises. So you would do, I have some promise, then I call .then, and then let's say I have something that depends on this in here. Then, maybe I'll create another promise. Something that depends on value. And then I call .then on that. I think actually they had like syntactic sugar, because then it was just a function. So this, you could also return this, I think, and then do .then in here, something like that. But the point being, a common problem in JavaScript was, I think this was callback hell. Was the term for that. Maybe? Yeah, something like that, like this. Oh yeah, not only promises, but also like lots of libraries had that as well. You would like read file, and then you give it a lambda that is called when that is complete. And then here you do parse data of that data, and again, you pass in a lambda. So by having these kind of side effects, you would nest your code even more, Yeah, you could kind of factor that out into top-level functions, similar, by the way, to what I did in here. I have this function ask for number instead of inlining that directly in here. And I could similarly, put this thingy into its own function, and then have ask for number, and then have, well, actually, print what's your guess, and then ask for number, turn that into a function, and it just prints something, and then it calls this other function ask for number that then only contains this code. I could factor this big function into multiple smaller ones, but that doesn't really solve the problem. The problem is that, we want to make that code look more linear, basically. And a solution that Rock had is, I think now they changed things a lot, actually. Yeah, they kind of completely changed their syntax and stuff. I actually like the previous one a lot more. But anyways, yeah. The idea was that actually, let me... I don't think there's an old tutorial page here. No. Rock also had tasks. Maybe not. Hang on. There. I read through that once, and they had tasks. That's where I stole the term from, by the way. So, well, anyways, yeah, the idea was that there's a way to turn the rest of a function body into a lambda. So let's kind of show how that might look like. What Rock did was they invented a new syntax, something like this, where you can have this sort of thing. And what this means is if you have a line that starts with, you know, basically a lambda, but then a backwards arrow, and then this on the right, that has to be a call, and basically the lambda is passed in as an extra last argument to that call. So in this case, this would be similar to calling print with 2 arguments. What's your guess? And then a lambda that takes no arguments, and the rest of the function body would become a body of that lambda. And using that, you can kind of model your early returns. You can model these kind of functions, even functions that return something new, like this readLine functions, for example. You could do, yeah, basically this, flipping that arrow around, saying please read the line, and then like that. And you can see how this makes the code quite easy to read. You know, first print something, and then, you know, the rest of the function body here becomes part of the continuation lambda here. Then call readLine with a lambda that accepts a string and contains this body. And yeah, you kind of no longer have nested lambdas anymore. I think this is also nice for like what you use early returns for in other languages. Kind of, you know, let's say, actually let's look at the style library. I know there were some cases where the code is really nested. One case comes in mind, and it's the int to string, the int formatting here, down here. This is horrible, you know. And yeah, by now, you know, strings are no longer built into the language. Right now you can just create, I guess, a byte array directly by, you know, taking the byte of this string and then adding the digit to that, I guess. I can refactor this code, sure. But in other languages, when you would have your if chains, like in Martinez, I could have something like if foo is A, then do something, you know, maybe even multiple lines, else if foo equals B, then do something else, else if foo equals C, then do something else. And this works, even though, you know, this only works because Martinez is not indentation based. Really though, what happens here is that this is, you know, if it's just an expression, and you don't need braces around single expressions, but really what the compiler parses this into is something like this. You know, if foo is A, then do this. Otherwise, you know, if foo equals B, then do this. Otherwise, if foo is this, then do that. So you do have this nesting in here. It just isn't obvious because, you know, if you only have a single expression, and that expression is, you know, happens to be an if, you can like syntactically move that over here. Now, Plum is a language where this, you know, it's indentation based by design, and we don't have the ability to kind of reorganize code in a way that doesn't really reflect how it's, you know, kind of format code so that it makes sense for humans, and we understand that this is, you know, an if-else chain kind of, and we have learned that. But really, this is, you know, I think this approach of nesting stuff is technically more correct. But if we had something like, you know, digit is 0, and then maybe a function, actually I don't know, like a function if or something that let me just write down the type signature. Yeah, that takes a bool and then some t perhaps, and then like that takes two lambdas that both contain the same, both return the same t. Now you can kind of do this sort of thing. You know, if digit equals 0, done like this usually. Then we will return the string 0. Otherwise, we will do something else. You could write that in the code, and I think we could even like, add an overloaded version of that if you already have like an immediate value, so that you don't need to wrap that in a lambda. Then we could even allow this sort of thing. But with this backwards arrow syntax, what you could do is write something like this. Basically, if digit is 0, then do that. And have a kind of early return in the function. And I think that's quite cool. Yeah. I mean, actually, I think if could also just take a single argument and return a maybe, because on maybe we have an else function. And we could add an else function that takes a lambda. So then you could do this sort of thing. If something else, boom, this one. I don't know. I don't know about the specifics. The idea is that even if this is mainly used for tasks, I think there were some other use cases that might pop up. They might appear and kind of evolve as coding patterns when I add this syntax to the language. Yeah, so that's what I'll do. Prevent this sort of infinite nesting of functions and make tasks easier to use by adding this backwards arrow syntax. Yeah, actually that was just, yeah, the version where I kind of hypothesized how that could look. But I think we don't really need that anymore because we do have a kind of minimal version up here. We just want that to work. All right, let's fire up the terminal and compile that and see where that fails. Yeah, so when we try to parse a lambda, yeah, all right, so we see the backslash, we know, oh, you have a lambda expression in here. But then we expect parameters. Oh, actually, we pass this as the parameter name, and then we expect a colon afterwards. That's sure, yeah. So let's fix that. Let's say probably in lambdas in here. Parse lambda type, that doesn't change, all right. Parse lambda. Contains a backslash. Oh, yeah, one note, this works on a line parser. We want this to work on a bacon. So basically on a node in the tree containing the indented lines of the program. So this right here should not work inside, in here, for example, not inside an expression. You can only use this backwards lambda syntax at the beginning of a line, basically, because that makes sense, because it's supposed to return to turn the rest of the body here into the lambda body. All right, so what do we have here? We have parse param. I think parse param. What do we have? Name. Yeah, exactly. We do have some special casing to not parse that as an identifier, and I think we'll need to do the same thing for the backwards error. And then we'll get a different error in here. Takes a long time. Yeah, expected error. All right. So now the question is, we can't pass that single that single bacon node into a lambda because it may wrap the rest of the body. It's actually in, hang on, where's that? In here. Expressions, parse expressions, where we have these toast expressions. We parse the expression, and then if we do a switch or a dot on a new line on the same indentation, that can kind of extend the expression in here. But what we want to do in here is basically check if this can. Question is, does this return some sort of enum that tells us either this is an expression or this is this sort of lambda continuation thing? Which then turns the rest of the body into parsing that separately. That would be one option, changing parse expression. Another option would be to kind of check that first. Kind of do bacon dot parse backwards lambda or something like that. And then if that's some lambda, then do stuff else. Then actually do stuff and then break out of the loop. And this doing stuff then consumes. This is quite cool actually. Then we just say the body is something. And then we return immediately. This is getting better and better. No, we actually just break, I think. Anyways, the body would be the rest of the bacon. So this would be bacons dot slice, subslice, something like that, from I to the end. So without first I. That's a thing, I believe. And this is again a slice of bacon, so then we can do parse expressions. Something like that. And then we do expressions dot push a lambda. And that will be the last expression of the current body, because all the other expressions on the same indentation in this slice of bacon, all these other expressions, they become part of the body, part of the lambda body. Yeah, does it make sense to do this instead of making parse expression return an enum though? Yeah, for now, let's do that, I think. It might be weird if you, yeah. So if you have, something like this. this is actually just a lambda that returns 0, I don't know. And maybe you pass that into some function. As soon as you do this, yeah, when you want to pass this bacon, the first thing we try is passing a backwards lambda. That means you kind of pass all the arguments here. Then we say, oh, there's actually not a backwards lambda. And then we kind of say, oh no, this is not a backwards argument, a backwards lambda. And then we pass the expression, which passes this as a lambda again, passes all the parameters again, and then it sees the forward error and it's like, okay, fine, yeah, this is a lambda. That's the only, we are repassing the line, which I guess is okay. Yeah, that's probably fine, right? That's not too much of a performance impact, hopefully. Maybe I'm going to regret that later on, but yeah, for now I think this is the cleaner approach. All right, so on bacon we need pass backwards lambda, and then here we need to do something. All right, but this will be in lambdas, I think. So we have pass lambda of some bacon, and we'll also have pass backwards lambda down here. Pass backwards lambda of some bacon, and this is not actually a toast expression because this is only the lambda actually has a backslash, then the parameters and the body. Let's paste that in here. So the body obviously is what will pass here, but a backslash and parameters, that's kind of what this signature here returns, what that contains. Oh, plus basically the right side of the lambda, right? Like whatever is on the other side of the backwards arrow, we need to pass that as well and have that as the, not just have a toast lambda in here, but kind of pass that as an extra argument to whatever is on the right of the expression. Yeah, so let's not freak out. Let's do let's create a new struct. Backwards lambda toast. Backwards lambda. Sure. Boom. And what we do is we have a backslash because a lambda needs that. And that's a string that source. We do have the parameters, which will be a slice of toast params. We don't have a body, but we do have the surrounding call, basically. The thing on the right. So a toast expression. Yeah, and then this returns the toast backwards lambda, and that doesn't fit within the line limit anymore, so let's wrap that. Alright, here we create a parser, we consume a backslash, we build a list of parameters where we pass the individual parameters, then we consume the arrow like this. Yeah, this is actually fine. Yeah, we just say this. Yeah, if there is no backwards arrow, that's okay. Yeah, we'll just say this is not, this bacon is not a backwards lambda. Totally okay. We did all this parsing, but what are we gonna do, right? And then rather than the body, this will be the kind of the right expression of the lambda, I think. And that has to be a single expression. So we want to do this basically. Now, if there are no children, then we pass an expression directly on this line parser. That makes sense. Expected right side of the backwards lambda. Okay, otherwise we do, what do we do? Parser.ensure is at end. Okay, if we do have any children of this expression, you know, basically having some sort of multi-line, should be able to do this, I think. You know, like especially if this is a more complicated call or something. I think that makes sense. Yeah, we want to pass them. We want to see, are they empty? No, okay, then expected right side. Of the backwards lambda. Alright, and this will be the body of the children. Alright, so we have the right side, and then we just return passed toast backwards lambda. Which doesn't actually contain the body yet. Instead it contains the right side, which no, we don't need to put that on the heap. Just do stuff like that. Clean. Alright. Yeah, this returns not a toast expression, but that. Cool. Very cool. And then this toast backwards, and now we kind of need to, I don't even know, enhance that, or kind of like, what do we do with the right side of that, you know? I think we, oh, look at that. It's going to be similar to this dot, I think. Oh yeah, quite similar. Except that left is the lambda, basically. And then we want to add that to the argument, but not at the front, but at the back. Simple. So we actually want to create a lambda first. Yeah. Lambda is something. Lambda is this right here. A lambda with that backslash with those parameters, and the body, well, that's, you know, the past rest of the expressions. Makes sense. And then what we push here, that kind of depends on what's on the right side of the backwards arrow syntax. So if the right side is a call already, then the arguments will just be the call arguments. Actually, I think, you know, that's a list of toast expressions. And then we push all the existing arguments, and then we push the lambda as an extra argument. That makes sense. And then, yeah, we have this toast expression dot call. And in here we have the right side is not a call. Then that needs to be a lambda, for example, for the read line here. This is not a call. This is just a variable reference. But then we just assume that there has to be a function or a lambda or something that you can call. So the function will be the entire right side, the entire variable or whatever, and the argument will just be a single argument, the lambda. So this we'll call readline with a single argument, this lambda. Yeah, it's kind of weird that you can't select that in a textual editor without selecting readline here, but all right, so let's try that. All right, so first of all, this is a result, so we have to put a question mark in there. Second of all, the body, parse expressions is a body, as a slice of toast expressions, but I think the toast lambda needs a single toast expression of the type body. Oh, yeah. All right. I mean, and that's fine. So this is a toast lambda, where this is a toast expression dot body of those expressions put on the heap. I think that makes sense. Let's see if that compiles. Okay, but we're getting further. That's quite cool. Right is not in scope. 204. Yeah, true, because that is lambda.write. And same here. Oh, no, that's weird. Let's call this backwards, not lambda, because this is not really the lambda expression. This is just the kind of backwards expression containing the signature and stuff. And yeah, and lambda is the actual lambda expression. That makes more sense. Compiles the compiler. That's nice. Oh no, that seems like it's kind of stuck. Ooh, I don't like that. It's stuck during parsing. Well, all right, let's see. Oh, I might have an idea. So in the beginning, I is 0, and then we see, hey, this is, this is a backwards lambda. The first expression of the main function, this is a backwards lambda. So then we pass the body, which should be the rest of the function, but here we want to start with at I plus 1. We don't want to kind of reparse the same line again, parse that into a lambda that wraps a lambda that wraps a lambda, and so on. Yeah, that makes sense. I'm wondering, can I go out of... Okay, I is definitely less than the length of the expressions, because we have this gap maybe here, and then I plus 1 is... Oh, look at that. It's kind of... We can see that. And yeah, this number modulo 100 is 49, so that's the correct guess. So that's, you'll go with, I mean, 50 is a nice first guess, I guess. Yeah, okay. Okay, but it's working. You know, as well as before. It's still leaking memory, but sure. That was easy, surprisingly easy. I mean, it was just a syntax change, so it makes sense. Nope, I want to do Plum stuff. Other stuff, yeah. All right, so what I want to do is support backwards lambdas. Yeah, this really is quite cool, I think. You know what, let's kind of review the playground and kind of refactor more stuff in there. So for this one, for example, what you would normally do, I think, is this sort of thing. You print not a number, and then you ask for a number. That kind of, I'm not sure if that really adds clarity here. Doing that the other way around. Maybe not. You know, maybe this, for this kind of recursive case, we don't want that. That's fine. Yeah. Oh, there was something in formatting. Right. And that kind of requires an if, I believe. Do I want to put an if in bool? I think so. Yeah. If of some condition, then, and then a lambda that returns some t, else another lambda that returns some t. This entire function can then return t by just switching on the bool. If it's true, then we call the then lambda. If it's false, then we call the else lambda. Yeah, kind of like that. And then let's also have a variance of that for, yeah, if some condition bool. Yeah, where then is just a t directly. And really that just calls the other function, I guess, with a function that then returns the then value. And similarly, if the, well, if then is a lambda but else is a single t, yeah, then we just pass on the then, but we grab the else in the lambda. And finally, if both of them are just values, oh, that's kind of wonky. Because then this overload will always match this one. So if both of them are lambdas, oh, you can't actually do that, right? Can you? You can't. Huh. If both of them are lambdas, do we want the if to evaluate the lambda automatically, the corresponding one, or do we want the if to evaluate to the correct lambda? Well, I think we actually want to not do this, but instead just do that. You know, kind of eagerly evaluate those. Yeah, and then it's only have a separate version where then is a t, but else is a lambda. And here we basically just do something like this. Then, otherwise, we call the else. I think that's fair. Yeah. Oh yeah, let's also have if condition, then yeah, I don't know. I mean, I like kind of explicit switches, so I'm not sure how often I want to use that and how much I want to encourage that, but in the general case I'm going to use this. Just for these kind of early returns, I think it makes sense to have some sort of and for this it makes sense to refactor that into something even better, you know, into building the correct byte for the string instead of doing a lot of checks here. Yeah, I guess let's leave that as is for now, and then fix that later at some point. Yep. All right. I'm happy with that. Let's commit that. Add support for backwards lambda syntax. Boom. Amazing. And I think that's it for this video. And see you in the next one.